So welcome to episode 70 of the Stanford MLSys seminar series. Of course, this quarter we are partnered with the great CS324 Advances in Foundation Models. And as part of that partnership, we're very excited to welcome our guest speaker today, Stella Biderman. So Stella comes to us from EleutherAI and a couple other places. And she'll be talking about some really cool, exciting things in open models, mechanistic interpretability, and things like that. On the panel today, we've also got Michael. So say hi, Michael. Okay. Classic Zoomer energy, as our advisor would say. And then we've also got Percy today. So say hi, Percy.
Hello.
Also classic Zoomer energy. All right. Yeah. So with that, we're really excited to hear what Stella has to say today. So go ahead, Stella, take it away.
Great. Thank you. I'm excited to be here. So like he just said, I'm here to talk about mechanistic interpretability, or the way I like to think of it is reverse engineering learned algorithms from transformers. So there we go. So what is mechanistic interpretability? It is kind of like I said, transformers implement algorithms. And the idea is that once you've trained, and I don't mean the actual feed-forward algorithm of the transformer itself, but when you use a transformer to answer questions, it is implementing some kind of logical algorithm. And in general, we don't know very much about what that algorithm looks like, how it behaves. And so what mechanistic interpretability seeks to do is unravel that a little bit and figure out what is going on inside the transformer after it's been trained, so that it's able to execute these algorithms and like what algorithms it executes to be able to complete tasks. So why might you be interested in studying this? Well, I think it's an abstractly interesting question, but there's a couple more practical reasons. First of all, if we understand the algorithms that transformers learn, we can hope to design better transformers. There's evidence that there are some types of algorithms and some types of functionality that are easier for transformers to learn than others. There's a very nascent study of how we kind of induce particular training behavior from the data that we put in. And so getting a better understanding of what algorithms transformers tend to implement can give us ideas of how to design and train better transformers. And the other more practical reason is that people actually interact with these algorithms pretty directly every day. Which might sound a little weird, but whenever you see people interacting with transformers, there's often a strange kind of human-computer interaction behavior where people need to change or adapt the way that they do things in order to work best with the transformer. So here are two examples of this. On the left-hand side, we see an example of few-shot learning. This was with the GTP NeoX 20 billion parameter model. We provided some poor English, good English pairs, and it eventually, corrected the grammar. And if you just input this by itself, that would not tend to perform as well. And on the right-hand side, this is a tweet from a colleague of mine from about a year and a half ago when we were playing around with text-to-image synthesis models, where we had figured out that if you stick the word Unreal Engine or rendered in the Unreal Engine at the end of a prompt for a text-to-image model, the quality shot up, and it also took on a kind of particular aesthetic quality. These are both examples of ways that people that interact with, that use these algorithms in practice, need to behave in ways that are relatively unintuitive to humans. Most of the time, you don't think of, when you think of using a computer to answer a question, you don't tend to think of putting in many examples of answering similar questions before you can get the final question back. And more explicitly on the right, like we're putting in particular strings of words. Some of the ones that people use nowadays are rather arcane to kind of induce particular behaviors or particular aesthetic styles. And the better understanding we can obtain of how kind of the algorithms inside transformers work, the more we can smooth this process over for end users. So the first kind of line of research in mechanistic interpretability was pioneered by some people at Redwood and Anthropic AI with what they called circuits. And the idea of circuits was kind of directly inspired by this example on the left, where there's clearly some kind of data copying going on, or task copying, where the model's learning how to do the task from seeing it being done over and over again. And they said, well, maybe we can't explain like the entire transformer, but we can decompose it into parts. And each of the parts themselves, kind of how they work on the inside will be opaque and difficult to understand. But in terms of inputs and outputs, we can understand what those do. We can understand how they get wired together. And so they built this framework called circuits, which is really just that the different components are things that we don't understand, but we understand how they're wired together, and we can describe the input-output behavior of each of the components. And they started looking at what they could model with circuits. So induction heads was one of the first things that they had come up with, which is the idea that data needs to get copied, or information needs to get copied and moved around from the input into the output, which, as I said, is essential for understanding feature learning. Mathematical computations. This turned out to be a very useful framework for understanding mathematical computations. And surprisingly, some of like the classical NLP pipeline stuff, like parts of speech identification, entity linking, named entity recognition, is something that you can model relatively well with these kinds of circuits. So for an extreme example, this was work done by Neil Nanda, that I'm a huge fan of. He actually took a small transformer and learned how to do and taught it how to do arithmetic perfectly. And I really do mean like perfectly. It had 100% out of train set accuracy. The only limitation on this transformer's ability to do arithmetic was when the numbers got so big it couldn't physically be represented by the machine. And furthermore, he actually went and used the circuits framework to decompose and reverse engineer the steps that it took. So the model used the strange modular addition formula that comes out of doing a Fourier transform. And he kind of walks through here each of the different steps. But this was a very artificial context. So we know that in practice, transformers tend to be pretty bad at arithmetic. He trained a relatively small model on a massive amount of arithmetic tasks for a very long period of time, which is a very different kind of framework from what we usually do. So a natural next question is, if we can reverse engineer kind of this basic algorithm from a toy model, what can we do with real models? So indirect object identification in the wild is a really cool paper from Redwood and Berkeley that looks at the task called indirect object identification. So when Mary and John went to the store, John gave a drink to blank, somebody. And the correct answer here is Mary. This is the task known as indirect object identification. You have a prelude clause that has multiple objects, and then one of them is the answer to, or is the next token in the subsequent clause, and you need to figure out which object is supposed to be referenced in the blank. And they did this work remarkably using a real world, albeit pretty small by modern standards, transformer, the small G2B2. And what they found was that the model kind of implemented the following steps. One, list all people in the sentence, so Mary and John. Two, remove all people that appear multiple times in the sentence. This token here, the Mary should be masked, obviously. So John appears twice, Mary appears once. So you remove the token John, and then you return the remaining token Mary. And they give this kind of diagram, which is perhaps a good way to think about what circuits look like. So on the left-hand side, what you see is the string of tokens. And as the model goes through the tokens, each of these tokens get routed to these different transformer heads. And these are actually identified as specific transformer heads in the model. The numeric annotations beneath the descriptive names they've given them refer to specific positions within the layers and specific heads within the model itself. And so they identified some heads that they called the previous token heads, which activate and notice when a name has come up that has already come up before. They have these S inhibition heads, which remove from consideration the name that's come up before. And there's a couple other types of heads in this diagram because they studied kind of robustness. The models that they were studying were actually trained with dropout, which is something really interesting. It means that you need to be robust to ignoring some of the layers. And so the model actually developed this kind of very redundant setting where even if some attention heads were knocked out, then other ones would take over that role, even if they weren't normally activating for that time. And they kind of show that emerges due to dropout. So that's kind of the three basic steps. You identify the previous tokens, you cut out the previous tokens, and the induction heads here copy the remaining name Mary. So that's kind of like the kind of work people do with circuits. And now I want to talk about a couple other ways that people do mechanistic interpretability research. So AlphaFold 2 is a transformer-based model for predicting how proteins are going to fold. And it's phenomenally good at what it does. And very recently, a collaborative group of people from a bunch of different institutions, led by Harvard, and Cornell, put together OpenFold, which is an open source replication of the AlphaFold 2 algorithm, as well as some novel methodological improvements and some really interesting interpretability insights. So what we were looking at when we were doing this research was trying to understand how the transformer's understanding of protein sequences evolves over the course of training. So what the animation I'm about to show is a representation of the model's prediction of the output of the folded shape of the protein after it's been trained for a certain number of steps shown here in the bottom left. And over the course of training, it kind of evolves and gets more complicated. It's pausing here and rotating so you can see that it has a three-dimensional shape. And the thing that's really fascinating to me about this is that we can actually see visually that there are some discrete stages that the protein fold, and here you get to see the kind of full final structure towards the end. But there's several discrete stages. So at the beginning, it has this like very flat two-dimensional structure. And then it expands a little bit and it's a, oops. Sorry, I'm having trouble pausing this when I want to. Very flat two-dimensional structure. And then it expands it, but it's still pretty flat. It has like it does have a 3D kind of unfolded shape, but it is still pretty flat in the second phase. So here's the first phase again. Here is the second phase. It's still pretty flat. And then here's the third phase where you can see it really has some kind of like real 3D shape. And then in the final phase of training, it kind of fills out the details. So you can kind of see that these coils are becoming thicker. That's a representation of filling out particular types of details. And this occurs in kind of distinct phases. And each phase is conditional on not having the subsequent information roughly optimal. So for example, the thin two-dimensional representation of the protein is actually a nearly optimal 2D projection of the final structure. So this is very thin. It obviously doesn't look like what the final protein looks like, but it does look like a roughly two-dimensional projection of what the final protein is going to look like. And similarly, once it's in this phase where there isn't a whole lot of detail, the geometric structure here is basically correct. When it makes mistakes in the geometric detail here, it's actually overcompensating for the lack of the detailed structure. So it can do that in various ways. But by and large, this is like a nearly optimal representation of the shape of it. And so what we're able to see here is not just the fact that the model is predicting how proteins fold in particular types of ways, but we can actually watch sequentially how these behaviors arise. That first it learns how to predict this two-dimensional representation. Then it learns to inflate that into a 3D representation. Then it learns to fill in the details. And I think that understanding these training dynamics of the mechanisms by which transformers make predictions about the world is going to be really essential to kind of interpretability research going forward, especially as there's more of a focus on coming up with theories of mechanistic interpretability that can do something useful for people, that can give kind of advice about how to design better models and stuff like that. And so the third kind of mechanistic interpretability related topic I wanted to talk about is something called the Logit Lens, and subsequent work on that. This is actually very, very recent work. We submitted it to ICML on Wednesday. So the Logit Lens was from a couple years ago, and the idea was that someone wanted to understand what happens if you skip over some of the layers. So you pass through a couple of the layers, you read this from bottom to top. So you have the tokens, it gets embedded, you have a number of these transformer layers, and then eventually at some point you just skip over to the unembedding layer at the end. And I'm sorry, my camera of myself is blocking my ability to read my own text. And since each layer adds the output to the residual stream, this is kind of similar to saying just that you're going to set all of the ending layers to 0. And this actually surprisingly gives a decent interpretable guess at what the model is going to predict. So what you see here is kind of a visualization of the model's best guess after various layers. So we're showing every other layer here. So here's the input, and you see the model's best guess kind of refines, and eventually converges to the correct, or converges to the model's final outputs. And the color here represents the entropy of the distribution. So the bluer the colors, the more certain it is about this prediction. Unfortunately, this was developed when GTP2 is kind of the only widely available transformer model, and it turns out it doesn't work all the time. When EleutherAI trained and released some language models on the same scale as GTP2, the original creators tried the methodology and they got a mess. First of all, you can see that the model is highly confident basically the entire time. The entropy is consistently very low. And second of all, despite that, the tokens change at the very last moment. It converges to, for example, the word ba here. And then in the last 2 layers, that changes 3 more times. Or sorry, in the last 3 layers, that changes 3 more times to something else, despite the fact that it had been on a very low entropy token. And so the question of kind of what is going on, why does this methodology that was developed for GTP2 not work for these GTP Neo models, was something that people have been talking about for a while. And so there's a couple of distinct problems with the Logit Lens. So obviously it only works for some models, which we learned once those other models came out. It's also statistically biased. The prediction after layer I is not an unbiased prediction of the final model output. Sometimes it produces nonsense up until the very end. And so what we came up with is something that we called the tune lens instead, where the question was, what if the unembedding matrix, I was saying that what this does is it takes the unembedding matrix and it applies it to the logits after some layer. So you take the outputs from layer 15, and you run through the unembedding matrix, and this is what you get, this line right here. Question is, well, maybe that's the wrong unembedding matrix to use. Maybe the different layers of the transformer, quote unquote, speak different languages. And so what we started doing was we started training different decoding layers for different decoders for different layers, which basically allows you to translate between layers. And kind of the intuition here is that these decoders that we're training are affine transformations from the output space of a particular layer to the unembedding matrix. And affine layers are free for transformers to implement. They kind of come for free at the beginning and end of every transformer layer. And so adding an extra affine layer shouldn't add information. If you add an affine layer to a transformer's architecture and you train it again, you don't gain any capabilities there. And so when we went and used this, what we found was that it was a much better and much more consistent way of decoding these models. So on the left, you see the original Logit lens, and on the right, you see the tuned lens, where we're basically using awareness of the semantics of each of the different layers being different. And so here the y-axis, the x-axis is the input number, the input layer number, and the y-axis is the perplexity of the predictions. And so the fact that these curves are much lower down indicates that they perform much better. And what we've actually been able to identify is that there are multiple different typologies of models. So despite the fact that there are a bunch of organizations that have been training large transformer models, they all use slightly different approaches, slightly different hyperparameter choices. And these kind of cause pretty substantial qualitative differences in the way that the models behave under each lens. So here, we're looking at the EleutherAI's GTP Neo models, where all of the models improve performance substantially using the tuned lens. However, in the OPT models developed by Facebook of the same sizes, we don't see that. We see that the smallest model improves a bunch at the very, very early stages. But by and large, these graphs look roughly the same. The very first layer is extremely different. There's an argument that our method cheats in the very first layer. But after that, they work very much the same. And so you can develop this typography of the different of how transformers behave differently based on whether they perform similarly or differently between the Logit lens and the tuned lens. And what we found is that there's a relatively robust typography. There are some transformers that go one way. There's some where the behavior is very similar, and there's some transformers where the behavior is very different. And kind of a lot of our ongoing work is trying to understand what is kind of the cause of that. And in particular, trying to tie that to pre-training choices that researchers make. I think that's the end of my slides. Yeah, I'm gonna hop off the, yeah. Yeah, that's what I have, I suppose.
Great. So we can go ahead and start the Q&A. I think we've got a lot of great questions from the students today. But I just want to kind of get started. So also a reminder to everybody listening on in the YouTube chat, if you have questions, feel free to post them in the chat, and we'll get them to Stella. I wanted to start off with just some questions that I guess I had that I was really curious about as I was listening to your presentation. One of them, I thought that the OpenFold demonstration that you showed, where you showed kind of how the training dynamics were evolving and what kind of concepts the model was learning over time. I was wondering, have you done similar analyses for kind of language models, any of those GPT style models? Is there anything that you've seen there as you watch these models kind of learn and evolve over time?
That's a great question. So this is something I've just started to study in language models. Just really earlier this month, we finished, or I guess last month, we finished training and releasing a suite of language models that was kind of designed in part to study this question that we're calling Pythia, which has a lot of scientifically useful properties in terms of consistency. A lot of the previous model suites have various forms of inconsistency. The checkpoint frequency varies from model to model, the training data order, or sometimes even the training data contents varies from model to model within the suite. And so in order to kind of help people ask and answer questions like that, we sat down to try to design the most consistently designed and trained suite so that you can really control for everything other than model size as you kind of compare the behaviors of different models. Because we really do think that or at least I really think that the operative question of interest here is not just how does a language model learn over the course of training, but it's how do you want to look at how a language model learns over the course of training and look at the patterns in kind of the behavior over the course of training, and then look at how those patterns of behavior change as the model scales. And so we've looked at this a little bit. There's a paper I have under review right now that's looking at memorization in language models. So one really curious thing is that there's a lot of literature on predicting kind of on like scaling laws for memorization that look at the total amount of memorization. What percentage of your training corpus is going to be memorized by a model? But we actually don't care about the memorization of most sequences. Typically, there's like a small subset of the training data that's much more important to not get memorized because it contains PII, because it's copyrighted text we weren't supposed to train the model on in the first place, stuff like that. And so kind of using this frame, we kind of look at the memorization of specific sequences. And we find that we're actually able to, early in training, predict which sequences will be memorized late in training. and that you can't do this via scaling alone, and you actually do need to look at the evolution dynamics over the course of time.
Oh, that's really interesting that you can, so you're saying that you can predict at the beginning of training which sequences are going to be memorized at the end.
You can predict early in training, like in the first seventh, for example. If you train the model a seventh of the way, then looking at what is memorized by the model 1/7 of the way through training gives you a pretty good idea of what's going to be memorized much later in training.
I see.
But looking at a fully trained small model is a much worse predictor of what is going to be memorized by the end of training.
Interesting. So it's kind of, does that sort of vary based on, you know, your random seed, or, and is it just kind of looking at does it kind of like, I guess, vary based on random seed, or is it something, you know, specific to a particular training run, or is it something that is, you know, if I pick this set of layer norms, this set of parameters, this set of et cetera, this will be kind of consistent over time?
So that's something that we're kind of trying to understand right now. That's a very expensive question to answer. So right now we're kind of attacking problems that we don't need to train like 10 billion parameter transformers 5-6 times to answer whenever possible. But in general, what we found so far is that the identity of the data matters, that there are certain types of data that is much more likely to get memorized than others. And that something about it's not exactly the compressibility or the perplexity, but something about the contents of the data makes it more likely to get memorized. And we also have some unpublished results on text on image models that kind of says something similar. And those are cheaper to train, so they've been trained a couple of times, and we kind of see this being consistent over the course of training.
Yeah. Cool. That's some really exciting stuff. I want to turn it over to Michael for a bit so he can ask, you know, turn it over to students and ask some of the questions that the students have been wondering in the chat.
Yeah. So again, thanks, Stella, for the amazing talk. It was really interesting to see sort of all these different, I guess, ways of sort of interpreting these models and trying to understand them a bit. I guess sort of related to that question of the AlphaFold model learning, let's say these 2D projections first and then expanding to 3D, at least empirically. I'm just curious, like, so you mentioned that there is some sort of data, I guess, or characteristics of the data that would sort of help in terms of trying to understand whether data is likely to be memorized earlier or later. Are there other ways to think about like how to frame this in a formalized setting?
Can you try asking that question a different way?
Yeah, I guess like, so like you notice, or you pointed out, right, that like, and for example, the AlphaFold demonstration, the model seemed to learn like the 2D projections of structures first and then expand to 3D empirically. Has this process been sort of formalized or summarized in like a mathematical framework?
No.
Or just in empirical observation? Okay.
It's a largely empirical observation. Yeah. Making a mathematical framework around it would be phenomenal and fascinating, but hasn't been done yet.
Let's see.
Before we go to other questions from the students, I see that Percy has raised his hand in the Zoom. So Percy, do you want to go ahead and ask your question?
Yeah, thanks. Thanks for the great talk. I find this stuff really fascinating, the idea that transformers can, from data alone, learn all these abstractions and that you're able to read out from these mechanistic interpretability tools. I wonder, I mean, the thing that always I'm wondering about is how this actually happens. How is stochastic gradient able to, given just a fairly weak signal, actually learn how to, you know, the mechanisms for doing addition, or these algorithms for you know, looking at indirect objects, or we've done some stuff on like learning gradient descent or lasso. And I wonder, after doing all the interpretability work, do you have any insights into how this might happen? I know it's a very sort of broad question, but I think this is, you know, something really interesting about the I don't know, something about the universe here.
Sorry, I got muted somehow. I think we're very early in trying to understand the answer to a question like that. Stochastic gradient descent is a extremely complicated algorithm, not so much in terms of how it's implemented, but in terms of what it can do and what it can't do. It's extremely complicated, and arguably much more complicated than the transformers that we're trying to study. And so we're pretty far away from having some kind of like real understanding of how that works. There are some kind of high-level observations that people can make. So for example, the language model T0, which is a version of the T5 language model that was fine-tuned on task-structured data, tends to perform terribly in a few-shot setting. And kind of the explanation for this is that it was fine-tuned on task-structured data, but was only fine-tuned on task-structured data in a zero-shot context. And that this somehow kind of deleted or destroyed the model's ability to do few-shot learning. And you can contrast this with the Flan T5 paper by Google, where they kind of built on the T0 research and did something similar. But one of the things that they changed the types of prompts they gave. So they not only gave zero-shot examples, but they also gave multi-shot examples. They also gave chain of thought examples. And what they found was that by fine-tuning on these multi-shot and chain of thought examples, they had much better multi-shot and chain of thought performance. So I do think that to an extent, some of these behaviors are explicitly encoded in the data. That the stuff that we tend to train transformers on has latent structure that kind of gives some of these capabilities in and of itself. I think that most people's mental model of the data that transformers get trained on is kind of that it's like conversations and it's books and it's academic papers. But if you actually go and like read carefully through the data that transformers get trained on, there's a lot of repetitive stuff. There's a lot of strange boilerplate stuff. And honestly, like, I think that there's a very good chance that some of that is explicitly causing some things that we now view as desirable behaviors, like this multi-shot learning, by demonstrating kind of text copying and stuff like that. But this is very, very speculative, and we're very far from having any kind of robust understanding of what that might look like.
Yeah, there's kind of, just to follow up, I mean, there's two aspects, right? One is whether the data has enough signal. And it seems like based on what you say, there's actually an extremely wide, diverse set of different data that could possibly lead to intercontext learning. And since that next word prediction is sort of like a universal objective, like if you can do the next word prediction, you have to have extracted enough of a signal in principle. Then in principle, there's enough things there. And then the second question is, well, fine, the information is there, but how on earth is stochastic gradient descent through like a huge network able to actually manufacture the algorithms, given that it's a horribly non-convex optimization problem and so on. And that's
same way it does everything else by magic.
Yeah, something like that. While you're training, like the fairies come in, and then if you're then good, dabble some, just tweak the weights around a little bit, and then you get to a good place.
Yeah,
that's a good explanation.
I actually had a follow-up on that conversation. So Stella, you mentioned that you've been looking at some of this early stuff on trying to figure out what a transformer will memorize by the end of the sequence. Do you see any patterns kind of that kind of match those kind of texts that you describe, where it's kind of does it ever memorize things that are kind of very repetitive or very text copying thing? Do you see those things getting memorized more often, or are there other trends like that you've seen as you've kind of done this exploration into what gets memorized and what doesn't?
So that's a bit of a weird question to answer, because we don't have great metrics for determining what has and what hasn't been memorized. And what we use in most of the research that I've done on this topic is a methodology introduced by Carlini and Catherine Lee and some other people at Google, where the idea is that you prompt the model with like a certain number of tokens from the training data set. And if it's able to continue the document and produce word for word verbatim what was in the training document, assuming, of course, there is some training document that corresponds to those tokens that you prompted it with, then it will, if it's able to do that for a certain number of tokens, then it counts as memorized. There's a kind of information theoretic problem with this, though, because if you prompt a model with 1, 2, 3, 4, one would hope the model would be able to continue 5, 6, 7, 8, 9, 10. And it's not clear that you want to call this memorization, or at least that you want to call this undesirable memorization. There's a sense in which the kind of intuitive understanding of what it means for a model to memorize something should mean that it's information that the model wouldn't have been able to kind of just produce on its own, that it memorized it in lieu of understanding the general pattern. And our metrics aren't very good at teasing these apart very well. So when you have like these very repetitive sequences, when you have like some arithmetic expressions, you do see very high memorization scores, but it's not totally clear how meaningful those memorization scores are. And if we had better metrics for memorization, whether we'd consider this memorized or not.
Right. There's kind of this confounding factor, which is if the model has learned the capability that you are ascribing to it, and you think that it's learned this capability because it trained on or memorized some pattern in the data, then, well, almost by definition, then it should be able to use the capability to do it. So then it's kind of unclear if it's kind of doing the memorization or it's just kind of demonstrating.
Yeah. And one thing I kind of want to work on to improve on this is tying it back to the logits themselves and saying, like, not only do you need to be able to reproduce the text, but you need to be able to produce it with high probability. And also maybe something like you need to be able to reproduce it and not reproduce something similar. So if you can go 1, 2, 3, 4, 5 and continue that on for the next 10 digits, but you can also do that for 1, 2, 3, 5, 7, 11, 13, or if you can do that for 1, 2, 4, 8, etc. Then maybe there's a general pattern recognition thing going on. That's not
Right.
That shouldn't be considered memorization. But if you have, if you're able to produce a scrap of code, an equation from someone's GitHub repository, many lines of code together, and you're not able to write code to produce similar sequences, or write code to solve similar problems, or write code to solve that problem just when not prompted with the like actual correct lead-in, then maybe that should be considered memorization. And it's kind of a philosophical argument as much as a technical one. It's something that we need to continue to kind of think about and sort out as research on this topic evolves.
Yeah, that's really interesting. As kind of another follow-up, so since you mentioned kind of that Logit view of it, I was, when you're talking about kind of the tuned lens method, I thought it was really interesting. One thing that kind of really stood out to me when you kind of compared the original Logit Lens versus your tuned lens formulation, with the originals, they kind of were very repetitive, would kind of say the same word throughout all the middle layers until the very end, would kind of switch. As you've kind of done the tuned lens work, have you come to any, do you have any more intuition or any more understanding about kind of what all those middle layers are doing in terms of how they're adding information? Is there anything that you've seen that kind of could give us some more intuition about kind of how that information is evolving throughout the model?
So I didn't really talk about this a whole lot earlier, just trying to give a quick overview of different areas and different topics. But one of the motivations for doing work like the tuned lens, like the Logit Lens, is to be able to say, so a transformer consists of a certain number of layers. And especially when you contrast it with like a RNN, those layers are the only things that can happen to it. Like there's a strong, so GTB3, so like a 13 billion parameter language model typically has 40 layers. And so there's a very strong sense in which there's only 40 things that can happen to the input text. Like there's 40 discrete steps the model takes, and then you get to the end. Now, each of those steps are very complicated, but there's only 40 of them. And you can they have to be happening sequentially. And this is very notably different from like RNNs, where you can apply things over and over again, and so kind of the ability to answer questions like that is one of the motivating reasons for why we're researching stuff like the Toon Lens. We view this as a tool that will likely be useful for kind of understanding that. One thing I'm especially interested in is kind of finding tasks where early in the model's unable to solve the problem, but is able to solve like a relevant subtask. And then later on in the model is able to solve the entire task. And so that kind of tells you that at some point in between, it added the capability to do the missing component. And we kind of have some preliminary evaluations along those lines, but it's messy and it's kind of hard to get really good results without designing your own custom evaluation sets, which is extremely time consuming, unfortunately. It's not something you can like hack together from publicly available evaluation data sets, unfortunately. But this kind of ability to understand how tasks are being composed and ideally locate where in the model, where in the layers of the model different functions are being implemented is like explicitly part of what we want to be doing.
Yeah, that's a really interesting question, and I look forward to kind of seeing more papers from you about that as we kind of understand these mysteries together. I want to turn it over to Michael.
Oh yeah, good.
Yeah.
I was just gonna say that there is a paper called. So there is a paper that does a lot of this kind of analysis on AlphaZero, the chess engine. And there's also a paper that kind of does some preliminary analysis along these lines in terms of language models, and also in terms of regular like image models. It's called Example Difficulty. Deep Learning Through the Lens of Example Difficulty by Baldock and a couple other people. Is a really interesting and provocative paper that starts analysis along the lines of. I'll drop a link in chat, which I hope means you can share it with people and such.
Yes, yeah, we got it. We'll share it with the students.
This is a early attempt at work along these lines, and I think that one of the things that we're currently doing is kind of replicating analyses like this using the Logit Lens and trying to kind of do a more careful job of locating in these large transformer models where different behaviors emerge.
Yeah, great. So I want to turn it over to Michael for a bit to ask some of the student questions.
Yeah, so a student is curious, sort of like as models, let's say, grow in parameters, how does this affect the ability for us to do mechanistic interpretation? Let's say, do smaller sort of toy models have sort of similar properties as larger ones? Stated differently, what kinds of tasks are hard to reduce or still defy all of our current, I guess, interpretation techniques?
So one of the big bottlenecks for mechanistic interpretability research right now is it's a lot of manual labor. If you want to be able to to kind of decode these behaviors, you need to just look at a lot of input-output pairs. You need to look at the activations. You need to look at what data gets sent where, and you need to just kind of do that enough until you can start noticing the patterns. There are some kind of techniques that can be used to speed up this process to kind of ablate over possible explanations, but it is a slow and unfortunately currently very manual process. And so the main issue with larger models is that as the models get larger, the amount of work that a human has to do gets larger. And I think that there are relatively large models that are within the grasp, especially in terms of like I'm thinking here mostly in terms of like the circuit stuff. Relatively large models I think are within human grasp, but most of the work has been done on smaller toy models. The other kind of big advantage of working with smaller toy models is that you can carefully control what the input data is. So in the work about perfectly learning modular arithmetic, they only trained on modular arithmetic, and they trained on modular arithmetic forever with a small model. And that's obviously not what happens with large language models. And so it's a proof of concept. It's a proof that a large language model can learn this information. But we also know that in practice it doesn't. If you pull up G2E3, if you pull up G2E NeoX, if you pull up Bloom, whatever you have, it will not know 5-10-digit arithmetic perfectly. And this is largely a statement about what's been trained on. Been trained on a lot of stuff that's not arithmetic. And so that's another really big advantage of working with small models, where you don't, where what you see is in some sense a much simpler world where you don't have cross-task interference.
Cross-cat interference.
This is my kitty cat, Merc. He's been very well behaved because he went an entire hour without getting in front of the camera.
That's great.
Just to follow up on that a little bit, I do wonder if you actually expose GPT-3 sized model to actually lots of arithmetic examples as well as the web, whether it would learn that. Because I think GPT-3, it's trained on whatever's on the internet, which I don't, probably doesn't have as complete of a data set for all the different tasks as if you like synthetically generated it. And also
Yeah,
training.
I think that GPT-3 is kind of is very likely to be explicitly trained on arithmetic, at least in part. In terms of kind of comparing the performance of models with and without this kind of explicit arithmetic encoding.
So just to clarify, by GPT-3 you mean Da Vinci or Text Da Vinci?
Who knows? The thing that's currently behind the API input.
Probably Text Da Vinci. The original GPT-3 paper, which is just a language modeling objective.
Yeah, so the original paper seems like it was very likely not trained on arithmetic and also not trained on code.
Yeah.
There's a blog post where they actually mentioned this that came out a month or two ago, where they changed over to pre-training on code, even for language applications relatively recently. But I would anticipate that. I mean, it's just really hard to say. Like, we don't really know what those models are doing. We don't even know how big they are a lot of the time, or how many tokens they've been trained for. So it's just really hard to say, and that's part of why I think that having access to open language models is so important, because people can actually know what they're studying and kind of know what is in distribution and what is out of distribution.
I completely agree.
Yeah. I guess another question a student is curious about is, are there ways that we can sort of, I don't know, impose, let's say, better interpretation downstream for a model when we're training or fine tuning it, such as a constraint that perhaps makes it more interpretable at the end of the day?
Yeah, so there's a couple things that people have come up with. So in the Logit Lens paper, one of the things that we recommend is people don't tie their embedding and unembedding layers. So that is a very common way to reduce the number of trainable parameters, which increases the effective power of the model, but it imposes some strange interpretability constraints. And we kind of go into this in a lot more detail in the paper than I was able to do in the 15 minutes I gave myself to talk about that topic. But one of the reasons why one of the things that explains kind of which models are reasonably understood using the Logit Lens and which ones are not is the use of tied unembedding layers. And it's kind of complicated, and I don't think we totally understand it, but there's a sense in which the unembedding layer in the embedding layer gives a privileged basis to the model itself. And this kind of over the course of the model, as you get further away from the embedding and unembedding matrices, you kind of decohere from that privileged basis. And geometrically, it does some strange things when you force it to end up in a circle and end up with the unembedding matrix being the same as the embedding matrix. That probably wasn't a great answer, but when the paper comes out like in a week, like, go read the appendix because the answer's there. Is, I guess, the better answer.
Sounds good. Thanks. Yep, we'll look out for it. Maybe as a last question, we're curious, our students are also curious, sort of, what are your thoughts on techniques to sort of automate or scale up some of these mechanistic interpretability, explorations or studies that you mentioned earlier can be very arduous, like sort of studies. A student brought up causal scrubbing, for example. Like, do you have thoughts on
Brought up
that?
what?
Causal scrubbing.
Yes. So causal scrubbing is something that I think is really, really interesting. Yeah. So I think causal scrubbing is a great technique for doing scalable interpretability work. Causal scrubbing is something that I use a lot of. It's something that a lot of other people have found a lot of success with. There are certain types of problems where that is a really useful technique. Same with knocking out attention heads. Some of the robustness studies that the interpreting circuits in the Wild paper did, where they were knocking out systematically the heads that they found, is a really good technique. A third really interesting technique is from the tuned lens paper, where what we do is we say, okay, we have identified kind of when you have when you use the tuned or the Logit lens to identify token prediction outputs, you can then say, okay, let's project everything to be orthogonal to what our current projection is. And you can look kind of how that affects the downstream propagation. So you stop halfway through, you predict what the current output is going to be, and then you go change it to move away from the thing you're currently predicting, and then you continue it through the model and you see whether the output changes a lot. And I think that kind of intervention-based approach is also a really powerful thing to do. Kind of the big limitation that all of these things have is that they don't reduce mechanistic interpretability to a number. It's not a benchmark score. And I mean, that's a good thing in many senses. It's a good thing because benchmark scores are highly limited. They conceal a lot of information. They're sometimes opaque to understand, but they are very scalable. So even when you have these kinds of techniques, you still need to apply them and look through the results and kind of understand what their outputs mean. So that these are very good techniques for decreasing the amount of work. But I would not view them as tools to use rather than ways to automate interpretability research.
Got it. Thanks. I wanted to kind of bring it up one step higher and kind of go a bit higher level for a second. I'm just curious, kind of what are you thinking about these days, and what is kind of next down the pipeline in the next year or the next few years in kind of this line of work, and what are you really excited about kind of seeing it, how it goes and how it develops as we get more open models, as these models maybe start becoming online and into people's hands more often. Where do you kind of see this line of work evolving, and what are you excited to kind of see going forward?
So, sorry, I was all queued up to answer the question, and then you changed it in a way that invalidated my response at the last moment. In terms of this kind of work, I'm really excited to see more people do it. I'm really excited to see more people play with things, more people build intuitions. One of the things that I regularly tell people is that the best way to build intuitions about how language models behave is to use them. I think that there are a large number, like even amongst people who do research on large language models, I think a lot of them don't spend enough time just putting in text and getting back text. You can really learn a lot and build very good intuitions from that. And that's not something that's been accessible, historically speaking, and it's not something that a lot of people have had the opportunity or even just like the awareness to do. And so as this stuff becomes more mainstream and as people have the ability to do more stuff like this, I'm really excited to just have more people, have more intuitions and to bring in ideas, because like right now there's a handful of institutions that are doing the overwhelming majority of this research. And I think that there's a lot of ideas that are going to be really obvious to outsiders, to people with different kind of biases, with different kinds of perspectives. And I'm really excited to learn what's obvious to those people that I'm missing.
Yeah, that's really exciting, and I'm definitely looking forward to seeing how that work evolves. So with that, I think we're nearing the end of the hour. I just wanted to say thank you again for coming on. You gave a really great talk. I think we all learned a lot, and we definitely enjoyed it. I think the students really enjoyed it as well. Yeah, so thank you so much for coming on. To everybody watching on YouTube, thanks for tuning in, and to all the students, of course, thanks for tuning in as well. We're very excited to be able to run this class and run this seminar this quarter. So this week, we actually have 2 talks on the seminar in the class. So we're also going to have a talk on Wednesday with Ludwig Schmidt from University of Washington. He's going to be talking about a data-centric view on reliable generation. So I hope that everybody tuning in now will tune in for that as well. I'm sure it will also be a really exciting talk. But with that, we're going to go ahead and say